Hello everyone and welcome to video number 2 in the three-phase circuits course, how a three-phase system is created. So how the system is formulated mathematically, how the system is generated physically. Let's start. To ease the concept of the three-phase system generation or formulation, we are going to explain it by analogy. Let us assume that we have a ceiling fan like this one, which consists of 3 blades. 360 degrees in the space, we are going to divide it by 3, so the blades are displaced 120 degrees apart. So they are 120 degrees. So when we are going to switch on the fan moves in a circular motion like this one, so it looks balanced. Assume that one of the blades is broken. The fan consists of 2 blades. So there will be a motion for the blades, something like circular motion, but there will be another motion for the fan pole, which is elliptical motion. So we have unbalanced system. So to have a balanced system, we're going to work that one by analogy. We need a 3-phase voltages. They are shifted by 120 degrees in time. So now let us put the 3-phase system in mathematical forms or function of time. So we have 3 phases. For example, phase A, between the point A and the neutral, we have a voltage VAN equals V maximum sine omega t. So we can write it in phasor form as VAN equals VRMS and angle 0. Regarding phase B, it's shifted 120 degrees, so VBN equals V maximum sine omega t minus 120. Or in phasor form, we can write it as VBN VRMS angle minus 120 degrees. For phase C, so we can write it as V maximum sine omega t minus 240, which is another 120 from the origin point 0. And in this case, VRMS angle minus 240. Or, because we have 330 degrees, we can write it instead of minus 240 plus 120. And in this case, VCN equals VRMS angle plus 120 degrees. So before I leave this slide, so remember that if I say VAN, so VEN equals VA minus VN, and we assume that the potential of the point N, which is a neutral, is 0. So sometimes you are going to find textbooks, they write it VN equals VA, because they consider that the neutral point has 0 voltage. So we can write it as VN or VA, VB, VC. So I can write that one VA equals VRMS angle 0, VB equals VRMS angle minus 120, and VC equals VRMS angle plus 120. They are the same, considering that the neutral point is 0 voltage. Please note that the voltage is the same for all the phases to have a balanced system. I'm going to explain first the balanced 3-phase system. 3 voltages, they are shifted by 120 degrees and they have the same amplitude. We noticed in the previous slide you mentioned that the potential voltage of the neutral point is 0. How do you know that one? We're going to prove that one mathematically. We have a 3-phase system balanced. VA equals VRMS angle 0, VB equals VRMS angle minus 120, VC equals VRMS angle plus 120 or minus 240. So definitely if we connect that one to a load, we have phase A current, phase B current, phase C current. So let's assume the currents will be I maximum sine omega t minus theta, sine omega t minus theta minus 120, sine omega t minus theta minus 240. If we connect the neutral point together, so there will be a neutral current equals IA of t plus IB of t plus IC of t. So we are going to add these expressions together. So if we assume omega t minus theta is angle x, so that one is x, I'm going to assume that one y. So that one is x, I'm going to assume that one is y. Using trigonometric identities, sine x minus y equals sine x cosine y minus cosine x sine y. So we are going to substitute in this equation. I neutral equals I maximum as a common factor. Sine x cosine y, cosine x sine y, sine x cosine y, cosine x sine y. So we're going to have that one as omega t minus theta and the angle. So sine omega t minus theta cosine 120. So cosine 120 is a number. Sine 120 is a number. So we are going to make a reduction for this equation. So that one will be I maximum sine omega t minus theta minus half, which is cosine 120, sine omega t minus theta, minus root 3 over 2 cosine omega t minus theta, minus half sine omega t minus theta, plus root 3 over 2 cosine omega t minus theta. If you notice, this term is going to cancel this term. we're going to add this one to this one, that one will be -1 and that one is +1. They are going to cancel each other. So the conclusion is, if we have a balanced system, the neutral current is 0. And in this case, you can have the potential voltage for the neutral point is 0. If you notice up to the previous slide, we formulated the three-phase system from 3 single-phase circuits. But now we can combine them in one circuit. So we have 3 lines and 1 neutral. So in this case, we have VA equals V maximum sine omega t, VB equals V maximum sine omega t minus 120, VC equals V maximum sine omega t minus 240, or plus 120. We have neutral current. If the system is balanced, neutral current is 0. Now we can put all the waveforms in one graph, function of time. So we have VA, VB, VC. They are shifted in time by 120 degrees. So in this case, if the system is balanced, the neutral current is 0, and in turn, the voltage for the neutral point is 0. If you'd like to know more about that one, you can visit the induction machine course, chapter 2, video number 2, induction machine terminals and slip speed concept. You explained how the three-phase system is formulated, but you didn't explain how the three-phase system is generated. Let's look for this diagram. So the main block here is the generator. So the generator can generate three-phase system, 3 voltages shifted 120 degrees. So speaking about electrical machine will be another course, but here we have the main element is the generator. But to have power transferred to this generator, mechanical power, we need something like a prime mover, can be from hydraulic power plants, fossil fuel power plants, nuclear power plants, or renewable sources such as wind power. Also, we can have renewable energy sources such as solar power energy, fuel cell, geothermal, and that one can lead to a generate voltage three-phase system. So the output voltage from the generator will be transferred to a transformer, and this transformer will be connected directly to a load, or the voltage output from the generator as a standalone connected to the load. But in some cases, the transformer is going to step up voltage, and then will be transmission through a transmission line, and then we have a step down transformer, and then we have a distribution station, and then we're going to have the power connected to the load. So the main part here is the generator. So we can generate the three-phase system or the three-phase voltages through a generator, something like synchronous generator, permanent magnet synchronous generator, for example. So each block of those will be a separate course, but our main target here that the generator can generate three-phase voltage shifted 120 degree in time. In conclusion, we can have three-phase system consists of 3 lines and 1 neutral wire, and the output will be for the balanced three-phase system is 3 voltages. They have the same amplitude and they are shifted 120 degrees in time. So the voltage Vn equals V maximum sine omega t, Vb equals V maximum sine omega t minus 120, Vc equals V maximum sine omega t minus 240 or plus 120. The neutral current and neutral voltage is 0. What will I watch in video number 3? In video number 3, we are going to cover the 3-phase configurations. See you in the next video.